Hello and welcome to Dr. Anima Upadhyay's Chemistry in Technology and Chemistry lecture videos. In today's video, we will learn the dimensionalities and the confinement of the electrons in various dimension systems of nanomaterials. So before we start this video, I would like you to please subscribe to my channel if you have not done it so far, and also to share this video among your friends. This video I have formatted in the question answer format for your better understanding. Let's begin with the definition of nanomaterials. So nanomaterials are considered to be the materials with at least one dimension that measures 100 nanometers or less. They could be in the form of particles, tubes, rods or fibers. What is a nanometer? It is a unit of measurement in metric system where 1 nanometer is described as 1 billionth of a meter. How are nanomaterials classified? Nanomaterials are classified either on the basis of occurrence in nature into two: natural nanomaterials and engineered nanomaterials, or on the basis of dimensions where at least one of the dimensions of the material should be less than 100 nanometers or less. And here in the table along with the image, I have tried to explain to you the dimensions along with their examples. Please go through it. Also remember, in my previous video on the introduction to nanomaterials, I have explained all these things in the question answer format. Please go through that video. I will give you the link of that video in the description box of today's video. What happens to the energy levels when atoms are isolated? The isolated atoms have discrete energy levels. What happens to the energy levels when atoms are in the packed form or in large numbers? When atoms are in packed form or they are in large numbers, that is in the solid form, the energy levels is split and they form bands, where band is a group of energy levels. Where does nanomaterials stand at energy level state? The nanomaterials represents intermediate stages between isolated and packed forms. What properties of nanomaterials are affected by electron confinement? The electron confinement affects optical, magnetic and electrical properties of nanomaterials. Is electron and quantum confinement same? Yes, they both are same. And why we have to study the electron confinement? Because the electrons play an important role in the dimensions of the nanomaterials, which affects the properties of the nanomaterials. What is the principle behind electron confinement? The Heisenberg uncertainty principle forms the basis of electron confinement. Why? Electron confinement in nanomaterials is an important process. Electron confinement is a process to locate the electron in an extremely small region, but it leads to an uncertainty in the measurement of energy and velocity of the electron, which goes according to the Heisenberg's uncertainty principle. As the region grows smaller, the idea of the position of the electron becomes better, but the uncertainty grows larger and larger. Thus, by decreasing the size of the region, a better position of electron is achieved, but not a precise measurement of the electron's velocity and energy, and this is the uncertainty principle. However, electron or quantum confinement is an important process that occurs in nanoparticles and is responsible for its important properties, which materials shows at nanoscale. Therefore, confinement is a direct consequence of uncertainty principle. What is electron confinement and how does it affect the energy levels and properties at nanoscale? If a particle is in a box of the order of the de Broglie wavelength of electrons, then the energy levels of the electrons change. This process is called electron or quantum confinement. Under this process, the electrons and holes, they get squeezed into a dimension that approaches a critical quantum measurement known as Bohr's radius. Thus, the electron confinement not only affects the energy levels of the nanoparticles, but also their electrical, magnetic and optical properties. What is de Broglie wavelength? The wavelength denoted by lambda is associated with an object in relation to its momentum and mass and is known as de Broglie wavelength, which is inversely proportional to its force. What is de Broglie concept of an electron? According to de Broglie equation, a matter can show dual nature. This means that a beam of electrons can be diffracted just like a beam of light. Thus, it acts both as waves as well as particles. Under certain conditions, a moving electron exhibits wave nature and are called matter waves or de Broglie or Schrödinger waves and is given by the equation x is equal to h by p, where h is Planck's constant and p is the magnitude of the momentum of the electron. At rest, the momentum of the electron is 0 and hence de Broglie wavelength would be infinity, indicating the absence of a matter wave. However, this is not possible according to quantum or wave mechanics. How many degrees of freedom are there and how many does an electron have? There are 6 degrees of freedom, 3 rotational and 3 translational, that is 6. But an electron doesn't have the rotational degree of freedom as it is a point particle. So it has only 3 degrees of freedom, that is only translational degrees of freedom. What is quantum confinement effect? When the length of a semiconductor is reduced to same order as the exciton radius, that is to around a few nanometers, then the quantum confinement effect occurs and the exciton properties are modified depending on the dimension of confinement. What are excitons? Excitons are coupled electron-hole pairs or quasi-particles formed by Coulombic force of attraction. What are the various kinds of confinement structures and on what basis are they classified? 3 kinds of confinement structures are defined depending on the dimension of the confinement: quantum wire, QR, quantum well, QW and quantum dot, QD. What does dimensionality refers to? It refers to the number of degrees of freedom in the electron momentum. This principle can be developed further by reducing the dimensionality of the electron's environment from a 2-dimensional quantum wire to a 1-dimensional quantum well and eventually to a 0-dimensional quantum dot. Does the reduction in dimensionality leads to change in the behavior of materials? Yes. The reduction in dimensionality into a thin semiconductor layer due to confinement of electron or holes leads to a dramatic change in their behavior. And this is the reason I have first explained to you the electron confinement before coming to the dimensionality. So explain the electron confinement and degree of freedom in quantum wire, quantum well and quantum dot. In a quantum wire, QR, the electron is confined across 2 directions. Thus, reducing the degrees of freedom to only 1. In a quantum well, QW, the electron confinement is just 1, thus giving it the degree of freedom as 2. Since the dimensions of the material along x and y are much larger than the critical length, the electron carriers experience no additional confinement effects and possess only 2 degrees of freedom. Thus, electrons and holes in quantum wells experience 1 degree of confinement and 2 degrees of freedom. Whereas in a quantum dot, QD, the electron is confined in all the 3 dimensions, thus reducing the degrees of freedom to 0. How degree of confinement and degree of freedom expressed mathematically? If the number of degrees of freedom is written as df and the number of directions of confinement as dc, then it is mathematically expressed as df plus dc is equal to 3. State the dimensionalities and the degree of confinement for bulk, quantum well, quantum wire and quantum dot. So here in the table I have described the structures along with the degree of confinement and degree of freedom. Bulk has a degree of confinement of 0, whereas the degree of freedom is 3D. The quantum well has a degree of confinement of 1D and degree of freedom is 2D. Quantum wire has a degree of confinement 2D and degree of freedom is 1D. Whereas the quantum dot has degree of confinement of 3D and there is no degree of freedom, which is 0. I have already explained in the previous slide about the degree of confinement and dimensionalities. Explain the role of quantum confinement in nanomaterials. In nanocrystals, quantum confinement produces unique optical and electronic properties that have great potential to enhance the power conversion efficiency of solar cells in photovoltaics. In quantum dots, it results in splitting of energy levels leading to increase in semiconductor band gap with decrease in size of nanocrystal. All materials including metals, insulators and semiconductors shows size dependent electronic and optical properties in the quantum size regime. The modification in the energy band gap of semiconductors is of fundamental as well as technological importance. Give examples of nanomaterials which are considered as next generation electronic devices. The semiconductors with widely tunable energy band gap are considered to be the materials for next generation flat panel displays, photovoltaic, optoelectronic devices, laser, sensors and photonic band gap devices. State the differences of 0, 1, 2 and 3D nanomaterials. The major difference according to the Cartesian coordinate system between 0, 1, 2, 3D nanocarbonaceous materials are: 0 dimension does not have any dimensions in Cartesian coordinate system. 1D have dimension in single Cartesian coordinate system. 2D have dimensions in 2 Cartesian coordinate systems. And 3D have dimensions in triple Cartesian system. Explain 0-dimensional nanomaterials with the help of examples. The 0-dimensional nanostructures are called quantum dot and are of the order of 2 to 10 nanometers. It is a semiconductor nanocrystal. It contains 100 to 1000 electrons or 10 to 50 atoms in diameter and are unique because of their size and properties. They find applications in composites, solar cells and fluorescent biological labels. What is the shape of quantum dots? The quantum dot could be cuboid, cylindrical, pyramidal, conical and lens shaped. Explain one-dimensional nanomaterials with the help of examples. One-dimensional nanostructures are called nanowires. Unlike other low-dimensional systems, nanowires have 2 quantum confined directions, but only one unconfined direction. That is, only 1 degree of freedom is available for electrical conduction, which causes change in density of states and allowed energy levels in nanowires. These easily play with the band gap, which is an important parameter in fabricating devices for specific applications. This property makes nanowires very useful where electrical conduction is required over tunneling support. Since the band gap increases with the decrease of nanowire diameter, nanowire can emit visible light with high efficiency. These are of interest, especially in solid state electronics and in medical sciences. What are the advantages of nanowires? Nanowires are of interest due to their asymmetric shape, which allows for tuning quantum effects in the short direction, but retention of bulk properties such as rapid carrier transport in the long direction. So it has both the benefits. Explain two-dimensional nanomaterials with the help of examples. The two-dimensional nanostructures are referred to as quantum well. Quantum wells are thin-layered semiconductor structures which are used to observe and control several quantum mechanical effects. A quantum well is a particular kind of heterostructure in which one thin well layer is sandwiched by two barrier layers. Here the electrons and holes both perceive lower energy in the well layer, hence the name potential well. This layer in which both electrons and holes are confined is as thin as 100 angstrom or around 40 atomic layers. Hence the fact that electron and hole are both waves cannot be neglected. The allowed states in this structure correspond to standing waves and are in the direction perpendicular to the layers. As only particular waves are standing waves, therefore the system is quantized and hence the name quantum well. They can be made to high degree of precision by modern epitaxial crystal growth techniques. State the applications of quantum wells. They are used in lasers, in measuring devices, as IR photodetectors, and in communication as high electron mobility transistor devices. Explain three-dimensional nanomaterials with examples. The three-dimensional nanomaterials are the materials that are not confined to the nanoscale in any dimension. They have a length, a width, and a thickness that are relatively beyond a few nanometers. This class can contain bulk powders, dispersions of nanoparticles, bundles of nanowires and nanotubes, as well as multi-nano layers. What are the applications of 3D nanomaterials? The 3D nanostructures are used as electrodes for electrochemical energy conversion and in storage devices. They also find applications in photoelectrochemical water splitting, photoelectrocatalytic solar to fuels conversion from nitrogen and carbon dioxide, rechargeable metal ion batteries and supercapacitors. What are fullerenes? Fullerenes are allotropes of carbon. It could be a hollow sphere, an ellipsoid, or of any other shapes. Carbon nanotubes CNT are also considered members of the fullerene family. Give the classification of nanomaterials based on dimensionalities with examples. So the nanomaterials are classified as 0, 1, 2 and 3 dimensional structures based on their dimensionalities, and here in this image I have given you the dimensional structures of the nanomaterials and their examples. The 0-dimensional structures examples are quantum dots, fullerenes. 1-dimensional nanomaterial structures examples are nanorods, ceramic crystals, carbon nanotubes, metallic nanotubes. The two-dimensional structures examples are graphene sheets, carbon-coated nanoplates, layered nanomaterials, and the three-dimensional nanomaterials examples are polycrystalline, dendrimers, liposome. State the dimensionalities in the following carbon allotropes: graphite, graphene, carbon nanotube, fullerene, and diamond. So the dimensionalities of carbon allotropes in graphite is 3D, in graphene it is 2D, in carbon nanotube it is 1D, fullerene is 0, and diamond is 3D. How do nanoscale dimensions affect properties of materials at nanoscale? Substances at the nanoscale level have a greater surface to volume ratio compared to the materials at bulk scale. This causes them to react very quickly. The small particles have a greater percentage of atoms on their surface, which accounts for their increased surface to volume ratio. So in my next video, we will discuss the surface to volume ratio in the nanomaterials. Thanks for watching this video till end. Don't forget to subscribe to my channel and also to share this video.